All right, now we're recording. Let's go ahead and start 3.3. We're going to use the information from the derivative in this section to determine several things about a graph, namely whether a graph on a given interval is going uphill, increasing, whether the graph is going downhill on an interval, decreasing, and then we're going to use the first derivative to determine where we have local max and mins. And when we do that, it's called testing critical values for local extrema. We call it the first derivative test. You will be tested over the first derivative test, okay? So how are we going to use the derivative to tell us if a function is increasing? Sit on top. If a function is increasing on an interval, what will we know about its derivative values? It's fantastic. If a function is increasing on a given interval, what would we know about the slopes, the derivatives? They're positive. So on any given interval, if your function is entirely positive, your derivative function, sorry, the function whose derivative it is will be increasing. If your function is decreasing on an interval, then the derivative is going to be negative and vice versa. And of course, if you end up with 0 for the derivative on any given interval, the function's constant. So what we're going to be interested in then is looking not for the values necessarily, but for the sign of the derivative on an interval. Is it positive? Is it negative? Is it 0? Okay, so here's just what we said. If this is an if and only if, so they're bidirectional. If a function is increasing on an interval, then its derivative is positive. If a derivative is positive on an interval, then the function is increasing monotonically or strictly. Same thing with decreasing, same thing with constant. Pretty easy idea, right? All right, very quickly, let's practice. The graph of the function is defined from -3 to 5. List the open intervals. We're not going to worry about endpoints where the function is increasing, decreasing, or constant. So, very easy. The function is increasing on what open interval? Yeah, -3 to 1. Decreasing on the interval from 3 to 5. And constant on the interval from 1 to 3. Pretty easy enough, right? Now, the reason I said open intervals is because we don't want to fight over the endpoints. If you go somewhere else, another professor, he might tell you to put all these as closed intervals, and that's fine, okay? It actually works. You could say at 3 the function is both constant and decreasing. They could fight over it. It doesn't really matter. I like to go with the open intervals. So just read the instructions. It might just kind of take the whole fighting over the endpoints out of the equation. All right, so another definition that we've seen before, a function whose derivative is the same sign on any given interval is said to be monotonic on that interval or strictly on that interval, strictly increasing, strictly decreasing, monotonic increasing, monotonic decreasing. We actually saw on that example from 2007, they used the word strictly, didn't they? Yeah, g of x was strictly increasing. So they prefer that over monotonic, but it means the same thing. We now ask ourselves at what values of x can a graph of a function change its increasing, decreasing status? Where can a function change from increasing to decreasing or decreasing to increasing? Any ideas? Well, let's come up here. This changed at x equals 1 and at x equals 3. Are those special values? Yeah, what are those values? They're critical values, right? Because the function is defined, but the derivative there is what? Is it 0? It doesn't exist. It's a sharp turn. What about the derivative here at 1? That one is also not 0. It's also D and E. It might be 0. It might be 0. Looking at it, the way I have it drawn, I'm sorry, this curve looks like it might be curving in smoothly. I'm not sure. I never really intended to come back and analyze whether if it was a cusp or not. But basically, if the slope from the left of 1 is not 0, like it is from the right, there would be a cusp. Okay? And it would be a critical value, right? Whether it was 0 or undefined. So that's what I'm trying to get at. A critical value is one possible place where a function can change from increasing to decreasing. Where else can a function change from increasing to decreasing? Don't say France. Where? Can it change at an endpoint? Not really, because then you would not know what's going on the other side. So you need to kind of look at some points on the interior. Critical values for sure. Anything else? Yeah, it's going to be when the derivative changes signs, for sure. Positive to negative or negative to positive. And that's getting into the first derivative test. Right now, at what values of x can that happen? Critical values, we said, or discontinuities, right? It can be increasing on one side and decreasing on the other. Now, the function is not defined there. Would that be a critical value at C? It wouldn't be a critical value, right? Because critical values have to first be in the what of the function? Domain. And a vertical asymptote usually is not in the domain. It's not a critical value, by definition, but it's still a very important bless you value, because that is another x value where a function can possibly change its increasing, decreasing behavior. Now, it could be something like this. That's another type of discontinuity. Is the function defined there? Yes. Would that be a critical value at x equals c? Yes, because the function is defined. There's a dot, but the derivative isn't, because it's not a continuous function. What about that? That's the same discontinuity as the function defined there? No. Does the function change from increasing to decreasing there? Yes. So that would be another important value, but not a critical value. So any type of discontinuity or any type of critical value is a place where a function can change its increasing, decreasing behavior. So here's an important idea. If f is a continuous function, continuous, that means no discontinuities, then the derivative can only change its sign at a critical value. And of course, critical values are places where the derivative is either 0 or undefined as long as it's in the domain of the function. A non-continuous function, a discontinuous function, can change its sign either at a critical value or at a what? Or at a discontinuity, like a vertical asymptote. All right. Example 2. Find the open intervals where this is increasing, decreasing, or justifying. And justify. Sorry, I'm watching the clock. This is a what type of function? Polynomial. It's continuous where? Everywhere. So there's no discontinuities. So determining where it's increasing or decreasing, I need the derivative, because I need to find the critical values. So I get 3x squared minus 3x. It's never undefined, so I don't have to worry about setting it equal to d and e. I'll set it equal to 0, factor out an x, and I got two critical values at 0 and 1. Now those are both critical values. If you know what the graph looks like, it's a cubic polynomial. It comes in the bottom and it goes out the top. It could look like that. And because I have two critical values, do I know what they are? This must be 0 and this must be 1. Do we have the answer, whether they're local or where it's increasing, decreasing? Sorry. Yes, but what if we didn't know what the graph looked like? Here's what you'd have to do, and this is a pretty typical thing. We're going to make a little number line chart, and we're going to test the intervals in between our two critical values. So I make a little number line like an x-axis, and I put my critical values up there. Now I'm going to choose just any random value from each of those intervals. To the left of 0, between 0 and 1, and to the right of 1, and I'm going to plug them into my derivative. And I look for the sign. You plug in a -1, you're going to get negative times negative is positive. Sorry, y'all can go. Plug in a 1/2, you're going to get a positive times negative is negative. Plug in a 2, you get a positive times positive. This tells you where the graph is increasing, decreasing, and increasing. Okay? Pretty typical thing. We'll pick up there tomorrow. Enjoy the rest of the day. Au revoir. Yes.